For this video, we will be focusing on molecular compounds and electronegativity. To brush up on some information, we know that bonding in atoms is atoms that strive to fulfill the octet rule, which means that they want a full shell of 8 valence electrons, or for hydrogen and helium, for example, where there are 2 valence electrons to acquire stability. For metals, they like to give away electrons, and nonmetals, they like to take away electrons. To begin this first problem, it is asking which is a compound with ionic bonds. As we know, ionic bonds are between metals and nonmetals, while covalent bonds are between just nonmetals. As we observe the first option, we see that nitrogen and iodine are 2 nonmetals. As well as for the second option, for carbon and fluorine, those are also 2 nonmetals. But for this last option, we have iron, which is a transition metal, which is still considered a metal, and a nonmetal, chlorine, which leaves us with the correct answer of FeCl2. For the second problem is asking when atoms need to fulfill the octet or duet rule, they may share electrons. The sharing of electrons between 2 atoms binds the atoms together. Such a bond is called a covalent bond. Opposite of the ionic bond, when atoms are bonded covalently, they make up a new matter called a molecular compound or molecule. The sharing of electrons can be represented by an electron dot formula, also known as a Lewis structure, where electrons are either depicted as a bonding pair with a line, meaning 2 electrons that are shared between the 2 atoms, or lone pair with 2 dots, meaning 2 electrons belong exclusively on that one atom. Draw the Lewis structure for the following molecules. For this first one, CF4. To start this, we begin to draw as this can be drawn based upon symmetry or electronegativity. For electronegativity, the least electronegative atom will be in the center. Then you will need to count the total number of valence electrons. For example, for C and F, we know that carbon is in the 4th group of the periodic table, so there will be 4 valence electrons, and fluorine is in the 7th group of the periodic table. And we see that there are 4 fluorines, so then you would times this by 4. So once you times this 7 by 4 plus 4, you would get 32 valence electrons, and now we begin to draw. So since carbon is the least electronegative, we will put that in the center, and there are 4 fluorines. You bond them with the central atom, so that gives you 2, 4, 6, 8 electrons, so that leaves you with 24 electrons. For phosphorus, we have 5 valence electrons, which gives us a total of 8. So here we would draw hydrogen, phosphorus, hydrogen, and hydrogen. Hydrogen needs those 2 valence electrons to bond, and that fulfills their 2, as phosphorus wants the octet rule, and we need to fulfill this 8, so there's 1, 2, 3, 4, 5, 6, 7, 8. Phosphorus is happy with 8, and each hydrogen has their own 2. For oxygen and fluorine, oxygen has 6, and fluorine has 7 valence electrons. However, there are 2 fluorines, so you would times this number by 2, which is 14. Adding that together, that would give you 20 total valence electrons. Since oxygen is the least electronegative, you would put that atom in the center, on each side making this symmetrical with those 2 fluorines. Here you would then bond the 2 atoms, and then that leaves you with 16 valence electrons left, so you will now perform the octet rule. 6 right there, 8, 10, 12, 14, 16, 18, and 20. So that is your total of 20. Each atom has their octet, and that will complete this. Continuing on, the first step in naming a compound is to recognize whether it's an ionic or molecular compound. Refer to the flowchart in figure 6.6 to help you name the following molecular or ionic compounds. So when you name molecular compounds, prefixes are used to indicate the number of a given element present in the compound. Mono indicates 1, di indicates 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. So for this first example, you would show that this is a covalent bond. And this first element here would be carbon. Since carbon only is 1, you would not put a prefix before carbon. And see right here, for fluorine, you have 4. So this is where you would use that prefix. So 4 is tetra, so you would write tetra as your prefix. And you'll put the base of the name, so this will be fluor. And then you put "ide" at the end. The next example is covalent bond. Here we have nitrogen. Since there's 2 oxygen, you would put di, ox for the base, and then "ide" to conclude that. And here we have 2 nitrogen. So at first, to begin, this is a covalent bond. Here, this would use a prefix, di, nitrogen. And since there's 1 oxygen, you would put mono. And then you would not put monoxide, you would put monoxide. Continuing on, you have FeCl2. This is an ionic bond. Since Fe is a transition metal, you do have to balance. And when you use a transition metal, you end up using Roman numerals. So this would be iron 2 oxide. My apologies, chloride. For E, this is a covalent bond. Here we have 2 nitrogen. So this would be dinitrogen. And here we have 3 sulfur. So this would be trisulfide. Lastly, for F, we have nitrogen and iodine. Here we see we have 1 nitrogen. So again, this is a covalent bond. So this will be nitrogen. We have 3 iodine. So this would be triiodide. For problem number 4, although atoms may share electrons in a covalent bond, one atom may be more electron greedy than the other. The atom that is capable of attracting electrons more than the other is the more electronegative atom. Electronegativity trends can be rationalized in the same manner as electron ionization trends. State the trend. So for this, if you look at the periodic table, electronegativity increases from left to right. And in the opposite direction, from top to bottom, electronegativity decreases from top going to the bottom. For these examples, phosphorus and chlorine. If you look at the periodic table, you see that chlorine is closest to the right of the periodic table, and that's where electronegativity increases. So chlorine would be more electronegative. For selenium and fluorine, fluorine is to the most top right of the periodic table, so that will be more electronegative. Moving on to C, nitrogen and hydrogen. Nitrogen is furthest right of the periodic table, where electronegativity is higher than the left-hand side, which is hydrogen. For D, we have carbon and fluorine. So fluorine is, once again, to the most right of the periodic table, which is more electronegative. We have nitrogen and iodine. Nitrogen is more electronegative because it is higher up most than iodine. And lastly, we have carbon and oxygen. Oxygen is, once again, most right of the periodic table, and this is repeated to the most right because this is the trend of electronegativity. In a covalent bond, the more electronegative atom can attract the electrons more, and thus the bond is more negative on one side than the other. This creates a dipole, two opposite ends, and the bond is further defined as polar covalent bond. How is a polar bond different from an ionic bond? So basically, a polar bond means that there are electrons shared between the two, but the sharing isn't even, so it is uneven. So this results in a partial negative and partial positive. So a partial negative can be seen as this sign, and a partial positive is the same, however, you just add the positive right there. And for ionic bond, the electrons are completely given or received to each other, so there's no partial. So you have a defiant part that is positive and a defiant part that is negative. To annotate the partial positive and negative ends, we can draw a partial positive or partial negative on top of each atom, and or draw a dipole of the bonds with a plus sign connected to an arrow. For the following bonds, draw a partial charge and the dipole movement of the bond. So for P and Cl, we see that this P is more positive than Cl, and for this, since P is more positive, you would do the partial positive and partial negative. Continuing Se and F, we see that F is more electronegative, so this will be the dipole direction. Se and F will be more electronegative, so that'll be partially negative, and Se would be partially positive. For nitrogen and hydrogen, we see that hydrogen is more positive than nitrogen, so we would draw this as so, and nitrogen would be partially negative, hydrogen partially positive. For carbon and fluorine, we see that carbon is more positive than fluorine, C and F. Here we will do the partial positive and fluorine partial negative. For the last two, you have nitrogen and iodine. Iodine is more positive than nitrogen, so you would write this, and then the nitrogen would be partially negative, iodine would be partially positive. For carbon and oxygen, carbon is less electronegative than oxygen, so you'll show their bond, and carbon will be partially positive and oxygen will be partially negative.